Hey guys, welcome to another video. Today we're going to be covering the topic of atomic structure in the IGCSE chemistry syllabus, and this is really important because it really builds the foundation of chemistry. So if you don't understand this, then you won't really understand anything else in the whole course. So this is really important. So without further ado, let's begin. So an atom is defined as the smallest particle of a chemical element, and a chemical element is basically a substance that is composed of just a single type of atom. For the sake of simplicity, let's take a look at the fact that you build a big yellow Lego wall simply just using these yellow Lego block units. Because this whole wall was built with just this yellow unit, this represents an element and this represents a single atom. If you had, of course, you've got different types of atoms. You could have green blocks, you could have blue blocks, and if you make a blue wall from just blue blocks, then that would be a different element from this one. Okay, so that's fairly simple. So the element carbon, for example, is only made of carbon atoms, and the element oxygen would only be made of oxygen atoms, and so forth. You do get the gist. So the structure of an atom is actually made of three subatomic particles. You've got the neutrons, the protons, and the electrons. Really important distinctions between these is, first of all, the charge. The charge of a proton is a positive one. The charge of an electron is a negative one. Neutrons do not have any charge at all. Secondly, the weight is also quite important. The weight of a protein is, given that it's relative to each other, just 1 unit. Neutrons also weigh 1 unit, and electrons weigh nothing at all. Okay, so this table here to the right summarizes this. Just be aware that this is the exact relative mass, 1 in 1840, but for the sake of your course, this is basically negligible. So you can say that electrons have 0 weight. Now, so the protons and the neutrons are located in the nucleus, which is the central part of the atom here, and the electrons are always in orbit of the nucleus, and they sort of lie in what we call shells, which are represented as ring-like structures that we draw around the nucleus. So let's take a look at that in a bit more detail. But before that, there's a couple of things that we need to go through. The number of protons is defined by the proton number or the atomic number, right? And in an atom, the number of protons will always equal the number of electrons, and that's really important. And that's the reason why atoms never have any charge, because the number of the charge from the protons will always balance out the charge from the electrons, making it a resultant charge of 0 always. If you have an imbalance in the number of protons and electrons, then it will have a charge, but at that point we don't call it an atom anymore, we call it an ion. So that's quite important, and we'll look at that in a bit more detail when we look at ionic bonding and things like that, right? The other thing is that the number of protons and the number of neutrons, when you add that together, we call that the mass number, because again, the mass is really only defined by protons and neutrons, because as we said before, electrons have 0 mass. Okay, so this is quite important because this is what the periodic table will tell us. So let's take a look at the electron arrangement just for a second. I've said that electrons are held inside these shells, and we sort of draw that as rings around the nucleus. So you've got the nucleus right in the middle here, and you've got the shells that are surrounding it. It's important to understand that the very first inner shell, which is closest to the nucleus, has a maximum capacity of 2 electrons. So you can't have any more than 2 electrons in the first shell. In the next 2 shells, however, you can have a maximum of up to 8 in each of these. So that becomes a bit more apparently important and useful for us when we take a look at the drawing out the diagram of different atoms later on. So this is a periodic table. The periodic table basically lists out all the elements that we know of, okay? And for example, we've got hydrogen here, helium here, all sorts of things. And the information that the periodic table gives us is quite important. So let's take a look at the element oxygen, for example. Let's zoom that up. So what you have is obviously the name of the element, and you've got the chemical symbol for the element, and you've got these 2 numbers here. So the top number, or the smaller number, is what we call the proton number, and we talked about this before. It's simply the amount of protons in a single oxygen atom. And this is the mass number, and remember, mass number is a sum of protons and neutrons. So just from this example, or this information that we have here, we can actually determine the number of protons, neutrons, and electrons in a single oxygen atom. So obviously the proton number is 8 because it says so. The neutron number is 8 because the proton number plus neutron number is 16 in this case, so there must be 8 neutrons. The electron number, as we discussed before, is always equal to the proton number in an atom, so in this case it's also 8. So when we put that into a diagram, you've got the 8 protons and the 8 neutrons inside the nucleus, and in the first shell, because it can only have 2 electrons, you put the 2 electrons there, and the rest is in the most outer electrons. The really important thing is initially just to draw the rings and fill in the electrons from the most inner shell. So ignore the rest, and first initially you just fill in the electrons from the most inner shell and then go outwards. So if this was blank, you would put 2 in, and then because you have 6 electrons remaining, you would fill that in the most outer shell. So you can see here that an oxygen atom has 2 electrons in its inner shell, and its most outer shell it's got 6 electrons, so 2 short of its maximum. So this brings us to the topic of chemical reactivity. Atoms have one single goal, and that is to achieve a full outer shell of electrons. So chemical reactions basically occur because atoms want to achieve this goal. So let's take a look at our oxygen atom, and we discussed before that an oxygen atom has 6 electrons in its outer shell. This means that it is too short of having a full outer shell. Remember, because this second shell can hold up to 8 electrons. This means that oxygen can achieve its goal in wanting a full outer shell in 2 simple ways. It's either you add 2 electrons into this outer shell, or you can remove 6 electrons so that this whole shell gets removed and it basically disappears, only leaving you with this inner shell, which of course has a full shell because it's got 2 electrons in there already. Of course, if you really think about it logically, which is easier, putting 2 or removing 6? Of course, adding 2 is so much easier, and in reality, removing 6 electrons never happens. It's always adding 2 electrons, and it does that either by sharing electrons with other atoms, which is what we'll talk about in future videos like covalent bonding and things like that, or it simply just gets it by process of transfer, and that's called ionic bonding. But again, we'll cover that in a topic in future videos. Okay, so that brings us to the next topic of what about these things here, right? So to the right of the periodic table, we call these noble gases. For example, helium already has a full outer shell. It's got 2 electrons in its most outer shell, which is also its inner shell, by the way, but it's only got 1 shell. And so basically it already has what it wants. So all of these elements to the right, these are called noble gases, and all of these, every single one of them has a full outer shell to begin with. That's why these gases are inert. In other words, they're unreactive, simply because they don't need to react with anything. They've already achieved their goal, and they're pretty happy with how they are. They're very stable elements, so therefore they're unreactive. So that just strengthens the idea that atoms really want to achieve a full outer shell, and that's why reactions happen in the first place. Columns, right? So you've got column 1, column 2, sort of ignore the middle here. You will learn about it in the future, but you don't really need to know it now. Column 3, column 4, column 5, and so on. And the columns are important, or the groups are important, because it tells you how many electrons there are in the atoms, well, how many outer electrons there are in the atoms within that group, right? So for example, in group 1, all of these elements here have 1 electron in its outer shell. All the atoms within group 7 have 7 electrons in its outer shell. And this is important because, as we talked about in the previous video, it tells you what an atom needs to do in order to gain a full amount of electrons, or full outer shell of electrons, because that's the goal of every single atom out there. So if you know, for example, fluorine, it's in group 7, so therefore it has 7 electrons in its outer shell. We know that it just needs 1 extra electron to make a full outer shell. So it would rather gain 1 electron than to lose 7, because it's easier that way. Here to the left hand side, for example, lithium here, it's within group 1, so it has 1 electron in its outer shell, and all it needs to do is remove 1 electron from its outer shell to obtain a full outer shell. If you're not familiar with this, go back to my previous video, have a quick look, and come back to this one after you're familiar with the concepts. Another really important thing is that you have metals and non-metals. Metals are the blue ones here towards mainly the left hand side of the periodic table, and the yellow ones are non-metals. The main thing is that non-metals usually have, you know, more than 4 electrons in its outer shell. So non-metals tend to gain electrons in order to achieve a full outer shell and therefore atomic stability, whereas metals tend to lose electrons because they usually only have 1, 2, or 3 electrons in its outer shell. They usually remove their outer shell electrons to achieve a full outer shell. So they have, you know, they do opposite things. Metals and non-metals do opposite things, right? So, you know, the metals in the middle here, they're technically metals and they're called transition metals, but you don't really need to worry about that at this stage. Pay more attention to the group 1 and group 2 metals, because those ones are the ones that are going to be popping up more and more often in your course. Okay, so the first thing that we're going to be looking at is the distinction between atoms and ions, right? So as I said before, metals lose electrons to obtain a full outer shell, and non-metals gain electrons to obtain a full outer shell. For example, in sodium we have, you know, it's in group 1, so it's got 1 electron in its outer shell. All it needs to do is lose that 1 electron to gain a full outer shell, because that outer shell simply disappears and it leaves it with 2 shells, and the outer shell now has a full set of electrons, which is 8 electrons in the shell. So when a metal loses an electron, that means it becomes a cation, right? Because it has a charge now. Remember, in an atom, the number of protons will always equal the number of electrons. Therefore, the charges always sort of cancel out. But in this case here, if the sodium atom loses 1 electron, that means that there will now be 1 extra proton, or in fact 1 less electron, and therefore there'll be more protons than electrons now. Therefore it will have a positive charge. So a positive ion is called a cation. Oppositely, in a chlorine atom, you have 7 outer electrons. All it needs to do is gain 1 electron, and when it does so, now that you have more electrons than protons, in this case 1 extra electron than protons, it'll become a negative charge, and a negative ion is called an anion. So basically, when an atom gets charged because it loses or gains electrons, it becomes an ion. And there's 2 types of ion. There's the positive one, which is what we call a cation, and a negative ion, whereby we call it an anion. So basically, metals, because they lose electrons, they'll always become cations, and non-metals, because they usually gain electrons, when they gain electrons and you have that electron-proton imbalance, then that's an anion, and that becomes really important. But if you look at this diagram here, the fact that sodium needs to lose a single electron and a chlorine atom simply needs to gain an electron, you see a possible win-win situation happening here. So that's exactly what happens. In ionic bonding, it's basically the bonding between metals and non-metals. Metals basically donate electrons to non-metals that really need it. So both atoms will obtain a full outer shell and become ions in the process. Cations and anions are obviously, they have different charges. Cations have positive and anions have negative charges, and therefore they are attracted by strong electrons electrostatic forces, opposites attract. So when that happens, we call that ionic bonding. So for example, here in this case, a sodium atom will happily donate its outer shell electron to the chlorine atom, which will happily receive it. So they'll both be happy because now they have full outer shells. Sodium becomes a cation, the chloride ion becomes an anion, and because they have opposite charges, they are attracted to each other. Similarly, a magnesium can actually form ionic bonds with chlorine as well. In this case though, the magnesium atom will need to lose 2 outer electrons in order to achieve a full outer shell. So therefore, it basically donates it, 1 to each chlorine atom. So the 2 chlorine atoms will happily accept those, and so they will all bond together via ionic bonding, and in which case 1 magnesium ion will combine with 2 chlorine ions, because there's 2 chlorine atoms that had received an electron each. So the chemical formula in this case would be MgCl2, signifying that for every magnesium ion there's 2 chlorine or chloride ions. So the previous diagrams sort of, diagrammatically tell you how things work, but in reality, the final structure of an ionic compound doesn't simply look like that. It looks like this, whereby ions, a lot of ions, they form a regular structure whereby the ions alternate from positive to negative, and they form a regular structure, and that's what we call a lattice. All these are ionic bonds. All the ions attracted to each other, held by ionic bonds, i.e. the electrostatic forces of attraction that they have because they're oppositely charged. But donating and accepting electrons is not the only way atoms can bond. So there's something called covalent bonding, whereby there's no donation or anything like that, but simply atoms share a pair of electrons, or 2 pairs or 3 pairs, right? So this is only this only happens between 2 non-metallic atoms. Okay, or several non-metallic atoms. The idea is that non-metals can share electrons with other non-metals to form covalent bonds. So by sharing electrons, all atoms will obtain a full outer shell. Take a look at hydrogen here. So 2 hydrogen atoms are sort of looking around, seeing if they can obtain a full outer shell, and they realize that if they share their electrons, like so, both hydrogen atoms now have a full outer shell because they've got 2. Okay, so these 2 electrons are shared amongst the 2 atoms. Okay, so this one now has 2 and this one now has 2, and so this is a sharing of a pair of electrons, and this is what we call a single covalent bond. In water, similarly, you've got hydrogens looking to achieve a full outer shell, and you've got the oxygen. Quite simply, if all of these shared a pair of electrons like so, you can see that oxygen has 8. Okay, so that's a full outer shell. And hydrogen has 2, and that's also a full outer shell. 2 is a full 2 electrons is a full outer shell for hydrogen, because this is in its first shell, whereas oxygen, this is in its second shell, and therefore it has a capacity of 8. So therefore it needs 8 electrons to achieve a full outer shell, and you can see that everyone is happy here. You don't always share a pair of electrons, though. Sometimes you can have 2 pairs of electrons being shared, and that's called a double bond. And if you share 3 pairs of electrons, that's when we call it a triple bond. There are a lot of different examples that Cambridge wants you to understand, and I've gone through all of this in the website www.freeexamacademy.com, so please check that out. And otherwise, we will move on to the idea of intermolecular versus intramolecular forces. This is really important, right? So here, this is a group of water molecules. Okay, this is what you find in a glass of water. The solid line represents intramolecular forces. This is basically covalent bonds, right? These are extremely strong. The bonds that you form between atoms inside the molecule are really, really strong. The dashed lines, however, are intermolecular forces. This is very different. This is the forces between molecules, not between atoms. So these bonds are much weaker. Now, when we boil water, we're breaking apart not the solid lines, but we're actually breaking apart the dashed lines, and this is really important. So that's why water isn't that hard to boil, because the dashed lines or the intermolecular forces between the bonds are not that powerful. That brings us to the topic of macromolecules. Macromolecules, on the other hand, are giant molecules where millions of atoms are joined to one another through intramolecular bonds or covalent bonds, right? So all these atoms are bonded through covalent bonds. Okay, so diamond and graphite are both examples of macromolecules of carbon. So the atoms, because they're all joined by covalent bonds, when you try to melt a diamond, you're actually trying to not break apart the intermolecular bonds this time, because they don't have any. You're trying to break apart the covalent or the intramolecular bonds, and that's why they are extremely hard. They have really high melting points. It's really hard to melt these things. Okay, so you do need to understand the properties of diamond, graphite, and silicon dioxide, and this too I have covered in the website, so go there for further detail. But basically, for diamond, you just need to know that the carbon is joined to 4 other carbon molecules. In graphite, each carbon is bonded to 3 other carbon molecules, and they have a layer-like structure like so. Therefore, they they have a slippery nature, because within layers, the layers are not, the attraction between each layer is not that powerful, so the layers can actually slide over pretty easily. But it's obviously fairly hard to break apart the atoms within each layer. Silicon oxide is fairly similar to the structure of diamond, and you can see the diagram as follows. And the last thing we need to look at is metallic bonding. So metallic bonding is basically what you find in all metals, right? In metals, atoms will remove their outer electrons and become cations. Remember, metals will remove their electrons to become or obtain a full outer shell, and therefore become cations. Cations are arranged in a lattice structure. Remember, lattice structure is basically another word for a regular sort of structure, like follows. And so the outer electrons are they're delocalized, meaning they can move sort of freely within the structure, and they form the sea of electrons. So what you have are a regular layer or regular arrangements of these cations, and a free delocalized sea of electrons surrounding it. So what happens is the cations attracted by forces of electrostatic attraction to the sea of electrons surrounding it, and this attraction is what bonds the structure together, and this is metallic bonding. So this is just a quick example, and these are named examples like zinc and sodium, and what it would look like at a molecular level if you were to zoom up on it. Okay.